Today we begin exploring one of the most important ideas in modern machine learning: feed-forward neural networks. These networks form the foundation of deep learning. Before we can understand more advanced systems like convolutional neural networks, transformers, or large language models, we first need to understand this basic architecture. A feed-forward neural network is, at its core, a system that learns how to transform inputs into meaningful outputs. You give the network information, data, measurements, or features, and the network learns how to convert those inputs into predictions. For example, it might learn to predict whether a transaction is fraudulent, it might estimate the price of a house, or it might determine whether an image contains a particular object. In this module, we will explore how these networks work, how they learn patterns from data, and why they remain one of the most widely used tools in machine learning. By the end of this module, you will understand how feed-forward neural networks operate and how to interpret them as systems that map information from the world into predictions and decisions. Let's begin. Let's begin by looking at what we will explore in this module. First, we will discuss what feed-forward neural networks are and why they are considered the most basic architecture in neural network design. Next, we will examine how information flows through the network and how data moves step by step from the input layer toward the final output. We will also explore the role of hidden layers and how they allow a neural network to learn useful internal representations of data. After that, we will learn how to interpret neural networks as input-output functions that transform information into predictions. We will then discuss how architectural choices, such as the number of layers and the number of neurons, influence the capacity of a model. We will also examine how training data shapes what the network ultimately learns. Finally, we will look at several real-world applications where feed-forward neural networks are commonly used. This roadmap will guide our exploration of how feed-forward networks transform data into predictions. A feed-forward neural network, often called an FNN, is the most basic and foundational neural network architecture. The defining characteristic of this type of network is that information flows in only one direction. Data moves forward through the network, beginning at the input layer and continuing toward the final output. Unlike some other neural network architectures, feed-forward networks do not contain feedback loops. Information never cycles backward through the network during prediction. They also do not have internal memory. Each prediction depends only on the inputs provided at that moment. Inside the network, inputs are gradually transformed as they pass through layers of neurons. Each layer performs a mathematical transformation on the data before passing the result forward to the next layer. Through this sequence of transformations, the network learns how to convert raw input data into meaningful outputs. Because of this structure, feed-forward neural networks are particularly well suited for prediction tasks, where the goal is to map inputs directly to outputs. Feed-forward neural networks process information one layer at a time. Data enters the network through the input layer. From there, it moves forward through one or more hidden layers before reaching the output layer. This sequence is often described as a flow of computation that moves from the input layer through the hidden layers and finally to the output layer. At each step, the current layer applies a transformation to the data and then passes the result to the next layer in the network. Because of this design, information always moves forward through the network. During prediction, there is no backward signal and no looping of information between layers. The network simply processes the input step by step until it produces a final output. A feed-forward neural network is built from three main components. The first component is the input layer. The input layer receives the raw data that we want the network to analyze. These inputs represent the features or variables that describe the problem. The second component consists of one or more hidden layers. Hidden layers perform intermediate transformations on the data. As information moves through these layers, the network begins to uncover patterns and relationships within the input. The final component is the output layer. The output layer produces the prediction or decision generated by the network. Together, these layers work as a sequence of transformations. Data enters through the input layer, is processed through the hidden layers, and eventually reaches the output layer where the final prediction is produced. In this way, the network creates a function that maps inputs to outputs. Hidden layers play a critical role in how neural networks learn. Instead of learning a direct relationship between raw inputs and final outputs, the network learns intermediate representations of the data. As information moves through the hidden layers, the network gradually transforms the input into more useful features. You can think of this process as a progression. The network begins with raw input data. Then it develops internal feature representations. Finally, those representations are used to produce a prediction. Each hidden layer refines the information it receives from the previous layer. Over time, these transformations allow the network to detect patterns that may not be obvious in the raw data. Through this layered process, hidden layers help the network build increasingly meaningful representations that support accurate predictions. To better understand representation learning, let's consider an example involving image classification. Imagine a neural network that is trained to recognize objects in images. In the first layer, the network might learn to detect very simple patterns, such as edges or lines within the image. In the next layer, those edges can be combined to detect more complex shapes. In deeper layers, the network may begin identifying parts of objects, such as wheels, faces, or corners. Finally, the output layer uses all of these learned features to determine the most likely category of the object in the image. Through this process, hidden layers gradually build richer and more meaningful representations of the data. Each layer adds another level of understanding, allowing the network to move from simple patterns to complex concepts. Another useful way to understand a neural network is to think of it as a mathematical function. In simple terms, the network takes an input and produces an output. We can express this idea as a function written as f of x equals y. In this expression, x represents the input data and y represents the predicted output. The goal of the neural network is to learn the relationship between the inputs and the outputs. In other words, the network learns how to map input features to a predicted outcome. Because of this ability to learn input to output mappings, feedforward neural networks are widely used for prediction problems in machine learning. Feedforward neural networks are commonly used for a wide range of prediction tasks. For example, in finance, a neural network might be used to predict credit risk by analyzing information about a borrower's financial history. In cybersecurity or banking, these networks can help detect fraudulent transactions by identifying patterns that differ from normal behavior. In business analytics, companies often use neural networks to predict customer churn, which means identifying customers who are likely to stop using a product or service. Feedforward networks can also be used to estimate house prices based on factors such as location, size, and property characteristics. In healthcare, neural networks may assist with medical diagnosis by analyzing patient data and identifying patterns associated with specific conditions. They can also be used in recommendation systems to score and rank products that may interest a user. All of these applications share a common idea. The network learns patterns from labeled data and uses those patterns to make predictions about new inputs. The architecture of a neural network refers to the way the network is structured. This includes the number of layers in the network, the number of neurons within each layer, and the connections between those neurons. These design choices determine how information moves through the network and how complex the model can become. For example, adding more layers allows the network to perform additional transformations on the data. Increasing the number of neurons within a layer gives the network more capacity to represent patterns in the data. Because of this, the architecture of a neural network plays a major role in determining how well the model can learn from the data. Choosing an appropriate architecture is therefore an important step when designing a neural network model. Model capacity refers to the ability of a neural network to learn patterns from data. A network with low capacity can only learn relatively simple patterns. These models are usually faster to train, but they may struggle to capture complex relationships in the data. This situation is often referred to as underfitting. The model is too simple to represent the true structure of the problem. On the other hand, a network with very high capacity can represent much more complex patterns. Larger networks with many layers and neurons are often able to model complicated relationships in the data. However, this flexibility also creates another risk, known as overfitting. In this case, the model may begin to memorize the training data instead of learning general patterns that apply to new data. Because of this, selecting an appropriate level of model capacity is essential for building effective neural network models. Neural networks do not understand concepts in the way humans do. Instead, they learn patterns from the training data that we provide. During training, the network observes many examples of inputs and their corresponding outputs. By analyzing these examples, the network gradually learns relationships that allow it to make predictions. Because of this process, the quality of the training data has a major impact on model performance. If the data contains errors or poor quality information, the model will learn those same problems. If the data contains bias, the predictions generated by the network may also reflect that bias. On the other hand, when the training data is diverse and representative of the real world, the model is more likely to generalize well to new situations. For this reason, in many machine learning projects, the quality and diversity of the data can be just as important as the algorithm itself. Training a feed-forward neural network is an iterative process in which the model gradually improves its predictions. First, input data enters the network through the input layer. The network processes this information as it moves forward through the hidden layers. Next, the network produces a prediction at the output layer. That prediction is then compared to the true label or correct answer from the training data. The difference between the predicted value and the true value is used to calculate an error. Based on that error, the model adjusts its internal parameters in order to reduce future mistakes. This process repeats many times as the network is exposed to more examples from the training dataset. Over time, the network becomes better at capturing patterns in the data and producing more accurate predictions. Feed-forward neural networks perform particularly well in many common prediction problems. One area where they are widely used is structured tabular data. This includes datasets organized in rows and columns, such as financial records, customer data, or business metrics. They are also effective for numerical prediction tasks, where the goal is to estimate a value based on several input variables. Feed-forward networks are frequently used for classification tasks as well. In these problems, the model predicts which category or class an input belongs to. Another common use is risk scoring, where organizations estimate the likelihood of events such as loan default or fraud. These networks are also useful for recognizing patterns in fixed datasets where the structure of the data does not change over time. Because of these strengths, feedforward neural networks are widely used in business analytics and predictive modeling. Although feedforward neural networks are very useful, they are not the best choice for every type of problem. Some tasks require neural network architectures that are designed to handle specific types of data. For example, convolutional neural networks, often called CNNs, are especially effective for image data. They are designed to recognize spatial patterns, such as edges, textures, and shapes within images. Recurrent neural networks, or RNNs, are commonly used for sequential data. This includes problems where the order of information matters, such as time series data, speech signals, or text sequences. More recently, transformer architectures have become the dominant approach for language processing and large-scale sequence modeling. Each of these architectures is designed to address different types of learning problems. Feedforward networks provide the foundation, but other architectures extend these ideas to handle more complex data structures. Let's summarize the key ideas from this module. Feedforward neural networks process information in one direction, moving from the input layer through hidden layers, and finally to the output layer. As information moves through the network, each layer performs transformations that help the model learn useful patterns in the data. Hidden layers play an important role because they allow the network to build internal representations that gradually become more meaningful. These networks can also be understood as systems that map inputs directly to predicted outputs. The behavior and capability of a feed-forward network depend heavily on its architecture, including the number of layers and the number of neurons within those layers. Training data also plays a critical role, since the patterns the network learns come directly from the examples it is given. Together, these ideas form the foundation for understanding modern deep learning systems. Before we can build a neural network, we first need to import the libraries that will allow us to construct the model and work with data. The first line imports the sequential model from Keras. The sequential model is one of the simplest ways to build a neural network. It allows us to create a model where layers are stacked one after another in a straightforward sequence. Next, we import two important layer types from Keras: input and dense. The input layer defines the shape of the data that will enter the neural network. In other words, it tells the model what kind of input to expect. The dense layer represents a fully connected layer of neurons. In a dense layer, every neuron is connected to every neuron in the previous layer. These layers are the main building blocks used in feed-forward neural networks. After that, we import NumPy, which is one of the most widely used libraries in scientific computing with Python. NumPy allows us to create and manipulate arrays of numerical data, which is essential when working with machine learning models. Finally, we import Matplotlib, specifically the PIplot module. Matplotlib allows us to create visualizations such as graphs and plots. In machine learning, visualizations are very helpful for understanding how a model is learning and how its predictions behave. Together, these libraries provide the tools we need to define a neural network, work with numerical data, and visualize the results of our model. Now that we have imported the necessary libraries, the next step is to define the dataset that our neural network will learn from. In this example, instead of loading a dataset from a file, we create a small dataset directly using NumPy arrays. The first line creates an array called X. This array contains the input values that will be provided to the neural network. The values range from 1 to 6, and they are stored as floating point numbers. These values represent the inputs, or features that the model will use to learn a pattern. The second line creates another array called y. This array contains the corresponding output values. In this case, the outputs are 100, 200, 300, 400, 500, and 600. If we look closely at the relationship between these two arrays, we can see a clear pattern. Each output value is simply the input multiplied by 100. The goal of the neural network will be to learn this relationship between the input values and the output values. Although this is a very simple example, it helps illustrate the basic idea behind supervised learning. We provide the model with input data and the correct outputs, and the network learns how to map one to the other. Before training a neural network, it is often helpful to visualize the dataset. In this step, we use matplotlib to create a simple plot of the input values and their corresponding outputs. The function p lt.plotopen parenthesis x comma y close parenthesis creates a graph where the values in x appear on the horizontal axis and the values in y appear on the vertical axis. Each pair of values from the dataset becomes a point on the graph. Visualizing the data helps us understand the relationship that the neural network will attempt to learn. In this case, if we plot the data, we would see that the points form a straight line. This indicates a clear linear relationship between the input values and the output values. Specifically, the output increases proportionally as the input increases. By plotting the data set, we gain an intuitive understanding of the pattern that the neural network will try to model during training. After creating the plot of our dataset, the next step is to display it so we can visually inspect the relationship between the inputs and the outputs. When the plot is displayed, we can see a straight line connecting the points in the dataset. Along the horizontal axis, we have the input values ranging from 1 to 6. Along the vertical axis, we have the corresponding output values ranging from 100 to 600. The line clearly shows that as the input increases, the output increases at a constant rate. This tells us that the relationship between the variables is linear. In other words, the output grows proportionally with the input. Visualizing the data in this way is an important step in machine learning because it helps us understand the pattern that the model will attempt to learn. In this example, the neural network will try to discover the simple relationship that maps each input value to its corresponding output value. Now we are ready to create and train our neural network. The first line defines the model using the sequential class. A sequential model is a simple way to build a neural network where layers are stacked one after another. Inside the model, we first define the input layer. The shape is set to 1, which means the network expects a single input value for each example. Next, we add a dense layer with one neuron. A dense layer is a fully connected layer, meaning the neuron receives input from the previous layer and computes an output based on learned weights and biases. Because this model has one input and one neuron in the output layer, it will learn a direct mapping from the input value to the predicted output. After defining the architecture, we compile the model. Compiling the model prepares it for training. Here we specify the optimizer as stochastic gradient descent, often abbreviated as SGD. The optimizer determines how the model updates its internal parameters during training. We also define the loss function as mean squared error. This loss function measures how far the model's predictions are from the true output values. Finally, we train the model using the fit function. We provide the input, data x, and the corresponding outputs y, and we train the model for 500 epochs. An epoch represents one full pass through the training data set. As the epochs progress, the neural network gradually adjusts its weights in order to learn the relationship between the inputs and outputs. Once the model begins training, the training progress appears in the output. Each line represents an epoch, which is one complete pass through the training dataset. At the beginning of training, the loss value is very large. This indicates that the model's predictions are still far from the correct outputs. As training continues through more epochs, the model gradually adjusts its internal weights. After each epoch, the model calculates the loss, which measures the difference between the predicted values and the true values in the dataset. If the model is learning successfully, we should see the loss decrease over time. In the output shown here, the loss values steadily drop from a very large number to much smaller values. This indicates that the neural network is improving its predictions as it learns from the data. This process of gradually reducing prediction error is the core idea behind training neural networks. Over many iterations, the model learns the relationship between the input values and the corresponding outputs. After the model has finished training, we can use it to make predictions. In this step, we use the predict function of the trained model. The input we provide to the model is the value 7. This value is placed inside a NumPy array because neural networks expect inputs to be provided in array format. When we call the predict function, the model takes this new input and processes it through the layers of the neural network. The network applies the weights and biases it learned during training to generate an output. Since the model was trained on the relationship between the input values and the outputs in our dataset, it has learned the pattern that connects them. In our training data, each output value was equal to the input multiplied by 100. Therefore, when the model receives the input value 7, it should produce a prediction close to 700. This step demonstrates how a trained neural network can generalize its learned pattern to make predictions on new data it has not seen before.